To graph or to find solutions for, find solutions to y prime equals 2x for three different initial values. And so those initial values were y of 0 is equal to -1, y of 0 is equal to 0, and y of 0 is equal to 1. So remember, the thing about differential equations are that a differential equation is an equation that relates a derivative with possibly, in this case, this one's a really basic one because we don't even have y anywhere in the equation, we only have y prime. But on our last example, the one up on the top side of the paper, we had y prime is equal to x squared plus y squared minus 1. And so the goal of solving a differential equation is to come up with a formula for y that satisfies the given equation. All right, and so we had a bunch of different solutions for our differential equation on the top of the page, and some of them were kind of swirly through the middle, and some of them were not so swirly, and so our solutions looked very different. What I'd like you to do now is take a look at those three solutions that you wrote on the bottom of this paper, and then show your neighbor what you have. And if you didn't happen to write anything down, then look at your neighbor's paper and see if you agree with what they wrote down. Okay, does anybody have a solution on your paper that agrees with your neighbor?
No, just curious.
Cisco, can you describe in words what your solutions look like? Okay, wait, let me get these. So take a listen to what Cisco has to say, and we'll see if we agree with him.
So they look like a bunch of parabolas that get closer at the top.
Does anybody agree with that? All right, so this seems pretty reasonable, and so just to confirm that we're all on the same page, when in our first example, y of 0 is equal to -1, I look for when x is equal to 0, y is equal to -1, so we can mark that point. That's the only point we have. That's the only fixed point we have, and everything from there is all about going with the flow. So these are all slopes, these are all tangent lines, and so I can kind of follow these guys along. It's very free-flowing, and your picture may not be exactly the same as mine, but it should be pretty close. You should never cross a tangent line perpendicularly. You should always be going roughly in the same direction as the tangent lines. And so there's a really rough parabola in there. And then we also have one at when x equals 0 and y equals 0, we have another parabola there as well. All right, so the moral of this story is that every single one of these solutions look like parabolas, and that totally makes sense because if I have y prime equals 2x, then what I'm looking at is dy over dx is equal to 2x. If I wanted to solve this differential equation, how could I do that? Yeah, we can just take an antiderivative, and so on the left side we'd have a y, and on the right side we have an x squared plus c. And so take a look at what these solutions are telling us. It's telling us that here's our solution, and we actually just solved our first differential equation. And so the solution is x squared plus c, and so x squared is your parabola, and where it is shifted vertically depends on your initial condition. And so there are some differential equations that you've been talking about ever since Calc 1, and here's an example of one of them. Okay. So moral of the story is that solutions can look very similar, and solutions can look very different. All right, are there any questions about the slope fields portion of the graphs? Charlotte?
So the y of zeros, those are the initial conditions?
Yes.
Okay.
Yeah, so these are initial conditions for 3 separate solutions.
Okay.
And so this would be our general solution here. And then, for example, y of 0 equals -1 is our initial condition. And then this would be our particular solution for that initial condition.
The particular solution is?
Well, it can be either the picture, or it can be, so when y of 0 equals -1, then I know that y is going to be equal to x squared minus 1. And so the particular solution that goes along with y of 0 equals -1 is...
Okay, minus 1.
Yep. Graphically is fine, or if we actually wrote x squared minus 1, it would also be legit.
Okay.
Okay. Other questions about the graphing of finding a solution to a differential equation via a picture? Okay. So solving a differential equation by looking at a picture is really useful for kind of getting your hands dirty and understanding what the general shape of these things are. But ideally, we'd like to be able to get answers that are actually analytical and actually have solutions to them. And so today, we're going to talk about one way to solve a certain type of differential equation. Again, there is an entire 4-credit class that will introduce you to all kinds of differential equations and all kinds of ways to solve these differential equations. We won't do that here. Here, I'm just giving you a flavor of one type. A formula for a solution to a differential equation. Some differential equations, and I highlight the word some, meaning not all. Again, there's a 4-credit class in differential equations. Some differential equations, DEs, can be written in the form dy over dx is equal to g of x times f of y. All right, so what do I mean by this? Well, if I can take an equation, a differential equation, and write it so that I have dy over dx on one side, and then on the other side, I can write it as the product of two functions, where one of the functions is a function strictly in terms of x, function just involving x, maybe some x squareds and some x cubes, maybe some numbers as well, but certainly no y's, times another function, which is a function just involving y's, then I've written my differential equation in this way. And so some differential equations can be written this way, and if a differential equation can be written in this way, it's called a separable differential equation. A separable equation or a separable differential equation. All right. So that's the type of differential equations that we're going to be looking at, strictly separable equations. So let's take a look at an example. Okay. So our example is dy over dx is equal to x cubed plus x cubed times y squared. All right, so I look at this equation here and I see a dy over dx, so I know that I'm talking about a differential equation. It's connecting x's and y's and dy over dx, so certainly a differential equation. It's order 1 because I only have a first derivative as opposed to a second or a third derivative involved in here. And so now I look over at my definition, which I just introduced to you, the separable equation, and that says, oh, if I can rewrite this equation up here as something in terms of x's times something in terms of y's, then I've got a separable differential equation. So when I look up here, the first thing I notice is the plus sign, which has nothing to do with multiplication. So right now, this is not written in the right way. So, anybody see any ideas here that we could rewrite that right-hand side?
Could you factor out the x cubed?
Yeah, we've got an x cubed in every single term, so we can factor that out and write this as dy over dx is equal to x cubed times the quantity 1 plus y squared. All right, so now I have written my differential equation as a separable differential equation. So I've got my g of x and my f of y. Okay, so part involving x's times the part involving y's. So here's how we solve what it is. To solve a separable differential equation, step number 1 is to get everything with y's on the left-hand side, and 2 is to get everything with x's on the right-hand side. Okay, so I'm going to rewrite my equation over here. I've got dy over dx is equal to x cubed times 1 plus y squared. Everything involving y's should be on the left-hand side, which means here it's 1 plus y squared. If I want to move it to the left side, I've got to divide. So on the left side, I have dy over dx times 1 over 1 plus y squared. And on the right-hand side, I have x cubed. So I've moved everything with the y's to the left side, and I've got my x cubed on the right side, but I need to move this dx over as well. So I need to multiply both sides by dx. And so what I end up with is dy times 1 over 1 plus y squared is equal to x cubed dx. All right, any questions about moving everything with x's to the right side, moving everything with y's to the left-hand side? Okay, so the right-hand side kind of looks like something that we're familiar with. The left-hand side is a little mixed up, so I'm going to reorder over here on the left-hand side so that I have 1 over 1 plus y squared dy is equal to x cubed dx. And when I look at this equation, it looks like there's something missing out of this equation. What looks like it's missing? Yeah, an integral sign. So let's go ahead and integrate both sides of this equation. So step 1 is to get everything with y's on the left-hand side. Step 2 is to get everything with x's on the right-hand side. And step 3 is to integrate. So here we go. We'll just throw an integral sign. If I do it to one side, I've got to do it to the other side. So on this left-hand side, antiderivative of 1 over 1 plus y squared.
That
One half the line.
tangent inverse?
Ooh, yeah, so not going to be a u sub because I won't have anything to cancel my derivative. But this guy right here is one of our known integrals. It's arctangent. So this is arctangent of y. And on the right-hand side, antiderivative of x to the third is 1/4 x to the fourth.
Tack on plus c's on both sides, or?
So that's a really good question. So far I've not tacked on any plus c's. Now technically the plus c on the left-hand side and the plus c on the right-hand side are going to be different. And instead of having an arbitrary constant on both sides, we're just going to take the arbitrary constant from this side and move it over. So what that works out to be is that instead of writing out plus arbitrary constant on one side and different one on the other side, I'm just going to forget about the one on the left completely and just write a plus c on the right side. So we have nearly solved this differential equation. Remember, the goal of solving a differential equation is to find a formula for y where y is some function of x, and whatever our choice for y is satisfies this equation right here. Okay, so I look back over at what we have over here, and we've got arctangent of y is equal to a quarter x to the fourth plus c. I'd like to solve this for y, and so at this point I've written y is implicitly defined as a function of x. You might remember implicit differentiation from Calc 1. And now we want to solve for x. So step number 4 is, if possible, solve for x. Okay, so if we want to solve this for x, I really did not mean to say that at all. Let me take that back. What am I trying to solve for here? I'm trying to solve for y. So, if possible, solve for y. So if we want to solve this equation for y, how do I get rid of this arctangent? Yeah, hit both sides with tangent, and so on the left side, I have tangent of arctangent of y, and on the right side, I have tangent of 1/4 x to the fourth plus c.
Why did you put tangent?
So arctangent is the inverse tangent function, so to undo the inverse tangent,
Oh, you just
I hit it with tangent.
So it just become white.
So on the left-hand side, our tangent and our arctangents cancel each other, and we are left with y is equal to tangent of 1/4 x to the fourth plus c. And notice the plus c is inside of the parentheses here now. It is not just tacked onto the end. And so this is our solution to our differential equation. And so if you want to, you can check that x cubed plus x cubed times y squared is equal to the derivative of this expression up here. All right, so this is our final answer. So final general solution. Are there any questions about that example? Okay, so we're going to look at a few more examples, but let's take our 10-minute break, and when you come back, we'll see a couple more places where we can use separable equations. Here's my final answer. What I need to do is see if our choice for y actually makes this equation true. So let's go ahead and look at the right-hand side first. So to check, we want to check to see if dy over dx equal x cubed plus x cubed y squared. We want to see if that equation is satisfied by our solution. So let's look at the right-hand side first. So our right-hand side is x cubed plus x cubed times y squared. And our choice for y, what we came up with for our solution, is we'll have x cubed plus x cubed times tangent of 1/4 x to the fourth plus c squared. So that's our right-hand side. Now our left-hand side is dy over dx. And so what that means is that I need to look at our solution y equals tangent of 1/4 x to the fourth plus c and take its derivative. And so when I take the derivative here, I've got to use the chain rule. So my derivative will be derivative of the outside, keeping the inside the same. So that's secant squared of 1/4 x to the fourth plus c. Derivative of the outside, keeping the inside the same, times the derivative of the inside. Now my inside, its derivative is x to the third. Okay, so I've got my right-hand side, and then I've got my left-hand side, and I look at them and see if they match, and it doesn't look like they do. So right now I'm kind of sad, because it looks like our solution is incorrect. However, yeah, there's a tangent squared over here, and there's a secant squared over here, so you might recall that 1 plus tangent squared theta equals secant squared theta so that I can replace secant squared theta with 1 plus tangent squared. And so my left-hand side looks like 1 plus tangent squared of 1/4 x to the 4th plus c, all of that, times x cubed. Okay? Any questions about that? So, do they look the same now?
Yeah, almost.
Almost.
You just distribute your x.
Yeah, you distribute x.
Yeah, if we distribute this x cubed through, then we'd have x cubed plus x cubed times tangent squared of 1/4 x to the 4th plus c. And that looks an awful lot like this over here. Now, over here I have slightly different notation, but this is still the same. The tangent of 1/4 x to the 4th plus c squared is the same as if I put that square right on the tangent. That's just a notational thing. So x cubed plus x cubed times tangent squared of 1/4 x to the 4th plus c. And so now, our left-hand side and our right-hand side are the same, and we are very happy about that. All right, so turns out that we do have a very good solution for our differential equation. Any questions about that?
So the logic for for getting the left-hand side was to take the derivative of the y value?
So in our original differential equation, which was this one here, the left-hand side was dy over dx, which says take the derivative of our y function.
Okay.
Other questions? Okay, so let's take a look at a second example. In this example, we've got dy over dx is equal to e to the y times sine squared x divided by y times secant x. And so what I see going on here is a bunch of multiplication and division. If I see addition and or subtraction, I have to worry a little bit. In our last example, when we originally saw addition, that is not going to work well for our separable equations. We need to have function of x times function of y. If we cannot write our equation in that way with multiplication between the function of x and the function of y, all bets are off and we cannot use this method. Okay? So we must be able to do that. So the first thing I'm going to do over here is on the right-hand side, I'm going to rewrite my right-hand side as a function of x, which will be sine squared x over secant x, times my function of y, which is e to the y over y. All right, so it looks like I do have a separable equation. I've got function of x times function of y on the right-hand side. And so now my method is going to be to move all of the y's to the left-hand side, all of the x's to the right-hand side. So moving my y's to the left-hand side means that I'm going to multiply both sides by y over e to the y. And so on the left-hand side, and then I'm also going to multiply both sides by dx. So I can really just do all of that at the same time. And so I've got y over e to the y dy is equal to sine squared x over secant x times dx. Okay, all my y's are on the left, all my x's are on the right. Any questions about that? A lot of algebra goes into these separable equations questions. Okay, so now that I've I've done this, I can go ahead and integrate both sides. So I've got the integral of y over e to the y dy is equal to the integral of sine squared x over secant x dx. Alright, so now looking at these integrals, neither of them are immediately straightforward. So I'd like you to think for a minute how you might analyze either side of the equation, pick your favorite side, and think about your very first step in terms of integration. Now turn to your neighbor and tell your neighbor what you're thinking about.
It's one of those, I don't know, let's try 2 or 3 minutes in, I'm like, hey, but then first guess as far as there's 1 over close to
All right.
So you just do use up.
So you've had a minute here to think about this. And the issue here is, unlike the last one, in the last example, bam, we could look at 1 over 1 plus y squared and then the antiderivative is arctangent. And bam, we could look at x cubed and say antiderivative is 1/4 x to the 4th. Both of these are going to require a little bit more thought. So I want to analyze each of these separately. So I'm going to put this integral on hold and analyze just the left-hand side to start. The integral of y over e to the y dy. Now, for those of you that were talking about this integral, anybody have a thought on the very first step on this one? Any thoughts?
Bring the e to the y up.
Yeah, bringing the e to the y up is a really good first step. So let's rewrite this as the integral of y e to the negative y dy. And then I might check for a u sub, but that's not going to work because the derivative of my power will not cancel my y. So if the u sub doesn't work on this side, what's our next idea? Yeah, integration by parts. And so integration by parts, I'm going to look at my acronym, LIATE. And so we don't have a log, no inverse trig, but we do have an algebra, so our algebra is our y. So we'll let u be equal to y. And then the dv will be everything that's left over, which is e to the negative y dy. All right, so our derivative of y is 1. Our derivative of u is du dy. So when I take my derivative here, because our independent variable is y in this case, we are thinking of du is equal to 1 dy rather than 1 dx. And our antiderivative, if I want to think about my antiderivative here, in my head I might be thinking about integrating e to the negative y dy and using the u substitution. And you can check that in your u sub, you end up with a v value of negative e to the negative y. You should double check that if you're not convinced. Okay, so now we've got all of our parts. Let's go back over here and we've got u times v, so that's y times negative e to the negative y minus the integral of v, negative e to the negative y du, which is a dy. And we've now set up our integration by parts. Any questions about writing that part down? Okay, so we can clean this up a little bit. We've got negative y e to the negative y plus the integral of e to the negative y dy. And then we can go ahead and integrate e to the negative y, which again you can do a u substitution on. Or you can say I've done 50 of those u substitutions where I have a number in the front, and I know that my antiderivative will be e to the negative y. So we have negative e to the negative y minus e to the negative y. And I'd really like to put the plus c on the end, but this is an intermediate step, so I'm going to wait until the end to do that. Okay, so we have just evaluated the left-hand side of this expression. Are there any questions about that part? Okay, so I'm going to go ahead and write that part down. We have negative y e to the negative y minus e to the negative y is equal to, and now we've got to work on the right-hand side. Alright, so our right-hand side looks like the integral of sine squared x dx, or sine squared x over secant x dx. And so, for those of you that were chatting about this integral, what were your first thoughts on what you might do with this integral?
Secant is 1 over cosine.
Sorry.
Alright, so secant x is 1 over cosine x.
So it just flips back up to the top here with sine squared x times cosine x.
Okay, so this seems like a really good option to start out with is, let's get rid of those secants, let's turn everything into sines and cosines. And so sine squared x over 1 over cosine. Once we flip that fraction in the denominator, we get sine squared x times cosine x. Any questions about that part? Alright, so now we look at this, and any thoughts on what we might do with this?
We can do a U sub for the sine, just for the cosine.
Okay, so a u sub, where u is equal to sine x. This seems reasonable. We'll have a u squared. Our derivative is going to cancel our cosine, so it seems like we're on the right track. So u is sine x, du over dx will be cosine x, which tells us that dx is du over cosine x. So replacing things, we end up with a u squared times cosine x times du over cosine x. And things cancel nicely for us. And we have the integral of u squared du. Everything is now in terms of u, so we can go ahead and take our antiderivative. We've got 1/3 u to the third plus c, although this is again an intermediate step, so we'll worry about the plus c's at the very end. Change our u's back into x's, and we have 1/3 sine cubed x. All right, any questions about the integral for the right-hand side? Okay, so we've done all that work off to the side. We can come back over here and write down that the integral of sine squared x over secant x dx is 1/3 sine cubed x. And at this point, I've done my antiderivative on the left, antiderivative on the right. I technically have arbitrary constants on both sides. They're different arbitrary constants, and I can move them together and just have 1 plus c on the entire integral. So we're no longer in pause anymore. Okay, so what we've just written down here is a solution for our differential equation where y is defined implicitly. Solution to the differential equation where y is defined implicitly. Okay, so we have an equation that involves x's and y's. Y is some function of x. And at this point I stop and I look at this and I say, okay, I would really, really, really like to solve this equation for y and have y is equal to stuff in terms of x. And I look at that and I say, there is no way that I'm going to be able to do that. This is just algebraically impossible. And in fact, there are certainly equations where it is algebraically impossible to solve for one of the variables. Here's an example of one of them. And so on this one, we are not able to solve for y. So we stop and leave our final answer as y defined implicitly.
So on the exam, are you going to want us to define y if possible?
That's a really good question. And here's how the question on the exam would be worded. I would say, solve the differential equation. And I would either say, here's how I will say this without telling you whether you can explicitly solve. I'll say, do not solve for y explicitly if you get, so I would say, suppose I gave you an example like this one and your final answer got to here in the instructions, I would say, do not solve for y explicitly. But if it's one like the last one where you can solve for y, then my instruction would be, if possible, solve for y.
Gotcha.
So if it says if possible, you
solve for y.
guarantee the problem.
Yes, that's right. You got it.
Oh, okay.
I have a stupid algebra question. So you can't just move the e to the negative y over and then divide both sides by e to the negative y to solve for
So if I move the e to the negative y over, it's going to be a plus e to the y.
Right.
So then I can't divide by it to cancel it out. Yeah, that's not a stupid question, it's a developer. Other questions?
Is what we just did, the function we found is the slope of what we were initially given. So we were given, so the first thing we were given is a rate of change.
Yes.
And then we found the function that gives that rate of change.
You got it. Okay. Correct. And not every differential equation starts out as rate of change equals stuff. It might be complicated stuff with rate of change mixed in the middle of all that complicated stuff equals other complicated stuff with rate of change mixed in there as well. And so, I mean, your differential equations can really explode into pure mayhem. But in the ones that we've looked at, we've had rate of change equals stuff. And so then what we found is the original function whose rate of change is described as.
If we graph that, it's the rate of change.
Yes, that is correct. Other questions?
So, maybe my algebra is bad, but term you can't just use, or log both sides to get rid of the e.
So thinking about logging both sides here, one thing that we could do is I would have, so maybe I might factor out an e to the minus y. So let's see here. So e to the minus y times negative y minus 1 equals all the other stuff. So if I wanted to hit both sides with log to bring that guy down, I would need to have this by itself. So I would first have to move this over here. And so yes, then I have e to minus y. And now I've suddenly got, so I could do log now, but now I've got a y here and I'm going to have a y on my right side and life is not good.
It just keeps getting.
Yeah, because now we're going to end up defining y in terms of y. So life is still not good. Other questions? It is completely and totally unsatisfying to not be able to solve this equation for y, and I totally understand that. But actually what this means is that this equation is more complicated than just a function of x. So for example, when you talked about implicit differentiation in Calc 1, you got to look at some really cool looking curves that are not functions of x, curves that do not pass the vertical line test. And that's exactly what we're getting here. If you are unable to solve for y explicitly, where y equals stuff in terms of x, that means that the curve, the solution that you get, is a curve which probably does not pass the vertical line test. And so that's what's happening here. Okay, so I want to wrap up this differential equations discussion with an example of a really, really important differential equation. Oh, and before we do that one, I do want to mention that the moral of this particular example is that all of your integration techniques from exam 1 still valid for exam 2. Important example of a differential equation. And this example that we're going to look at is the population growth model.
Oh, man.
So my guess is that you have seen the population growth model in a variety of settings. So a lot of what I'm going to talk about today will be very familiar to you. However, you may or may not have actually seen this from the perspective of a differential equation. Okay, so population growth model, also known as the law of natural growth and decay. All right, so here's how the model works. The idea is that population grows at a rate proportional to the size of the population. All right, so in order to write down a differential equation, in order to actually come up with the equation itself, what you need to do is to look at your experiment or your whatever you're trying to describe and be able to describe that situation in words. And that's what we've done here. We're describing this population growth model. This particular model is under the assumption that there are no restrictions on any sort of carrying capacities. Things like there's plenty of food, there's plenty of water, there's plenty of space for these creatures to continue to grow. And so our model is strictly based on the population grows at a rate proportional to the size of the population. And so we're going to use P as the population at time t. And the words that are describing the model up here, the population grows at a rate proportional to the size of the population, says that our growth rate, that's dp over dt, how does the population change with respect to time, is proportional to, so is equal to, some constant times the population. So our model in words can be interpreted into dp over dt is equal to k times p. All right, so where does this model apply? Well, this model applies to, like I mentioned, freely growing populations. Populations where they are not restricted by food or space or anything like that. In those types of situations, this k value is going to be positive. We can talk about radioactive decay. Things such as, for example, mass of a radioactive object decays at a rate proportional to the mass of the object. So if you swap out the word population and put in the word mass, then we've still got the exact same model, only in this case we're talking about decay, and so k is going to be a negative number. And then if you're interested in making money, this model also works for continuously compounding interest. Continuously compounding interest. If your savings account increases at a rate proportional to the value in the account. So the more money you have in the account, the more money you're going to make on interest. And so in the case of money, we're thinking of swap out the word population for amount of money in your account. So what is your account populated with? It's populated with dollars, we hope. And so in this case, we're hoping that your account will grow, and so we want the k value to be greater than 0. Okay, so here is our differential equation, and our goal is to come up with a formula for the population. So we're given that dp over dt is equal to k times p. Now there's a lot of letters going on here, so let's be clear about what is variable and what is not. In terms of this example, t is our independent variable. P is our dependent variable. Our job is to find a formula for population in terms of the independent variable t. So t is playing the role of x, p is playing the role of y in this example, and k is some constant that's a rate of proportionality, and that depends on the specific example that you're looking at. Okay, so when I look at this equation, I look at it and say, okay, can I write this right-hand side as a function of, before it was a function of x and y, as a function of t and a function of p? And over on the right-hand side, I don't even see any t's, so realistically, I suppose that I could write this as 1 times k times p, or I could even put the k over here as part of the t function. It doesn't really matter. I can put it either way. So I have lots of different choices. This is my g of t, that's my k, and my p is my f of p. So it's a little bit degenerate in the sense that these guys are not fancy functions of p and fancy functions of t. They're very, very basic functions. Okay, so now I want to separate, and so I want to move all my stuff involving t's to the right-hand side, all the stuff involving p's to the left-hand side. So I'll divide by p, and I'll multiply both sides by dt. And so we've got 1 over p dp is equal to k dt. All right, any questions up till here? Got it?
I'm not clear on why k is g of t if it's just a constant.
So we have a choice. The k can either be lumped in with the t function, which is just a constant, or we can put the k here and have g of t be equal to 1.
Oh.
Either way. So either I'm going to keep k here, or I'm going to put 1 over k times p over here.
Okay.
And either way it works. It's either way. Other questions? Okay, so now let's go ahead and integrate both sides. On the left side we have the integral of 1 over p dp, and on the right side we have the integral of k dt. Alright, on the left side, these integrals are a little bit easier than the last example we did. On the left side we have natural log of p, and on the right hand side, k is a constant, so its antiderivative will be k times t, and I know to use the t because that's the variable we're integrating with respect to. Alright, I've integrated both sides. I technically have a constant on both sides. I'm going to put them together over here on the right side. So I've got natural log of p is equal to kt plus c. Okay. So now we've got our equation, and right now we have a solution for p where p is implicitly defined. So this is where on the exam the instructions at the beginning would have said, if possible, solve for p. And so that says, solve for p. Okay, so here we go. If we want to solve for p, what do we need to do? Yeah, we want to take both of these sides and have e raised to each side. So we actually want to use Cisco's idea from the last problem. We'll use it here. Only the opposite direction. So we have e to the ln of p is equal to e to the kt plus c. So on the left-hand side, my e and my natural log will cancel each other, and I'm left with the absolute value of p. And on the right-hand side, I'm left with e raised to the kt plus c. Now we have not completely solved for p yet. We still have these absolute values on here. And so if I want to get rid of the absolute values, what these absolute values tell us is if the population is positive or negative or whatever, these absolute values are saying, and so in our example, yes, we're talking about populations, but it's possible in other examples that this value could be negative, so I want to explore what happens here with these absolute values. With the absolute values, if I want to get rid of them, that means that I need to include a plus or minus on the other side. So to get rid of those absolute values, I pay the price of a plus or minus. Okay, now I have solved for p, but for those of you who are familiar with the population growth model, this is not what it looks like. Okay? So we have a few more things to adjust here. And here's what will happen. I've got p is equal to plus or minus. If I've added the powers up here, algebraically, I can rewrite this as e to the kt times e to the c. And so now, look at what we have now. I've got this c, which is an arbitrary constant, which means that really, e raised to the c is still an arbitrary constant. And I've got this plus or minus in front, which is kind of arbitrary as well. And so I'm going to lump the e to the c and the plus and minus in the front all together into one letter and say we are going to let a be equal to plus or minus e to the c. So all those things are all constant values. We are going to lump them together into one constant value, which we're going to call a. And so what that does for us is it says now our population is equal to a times e to the kt. And now we have our population growth model. So the population growth model starts out with, well, started out with dp over dt is equal to k times p. Just the simple words of saying population, the rate of population growth is proportional to the size of the population itself. There's your differential equation. From there, we come up with an exponential growth model, which describes a lot of things: free population growth, radioactive decay, making a lot of money with continuous and compounding interest. All right, any questions about that example? Okay. All right. Well, that wraps up our differential equations section. Are there any questions about the differential equations? When you get into the differential equations class, some of the things that you'll be studying are those slope fields that we looked at. You'll look at that slope field as one entire function. You'll have families. So within one slope field, you have a whole bunch of functions. And then that slope field itself, you're going to be able to look at how the slope fields change based on things like changing your parameters, such as a right here. So that's going to change your entire slope field, and then you have an entirely new set of functions to look at within each slope field. So things start to get pretty complicated, but it's pretty cool. So something to look forward to is your differential equations class. Okay. So that wraps up the material that will be on exam 2. I want to give you a preview of our next section, and we won't go into much detail on this today. So yes, this is material out of chapter 6. We skipped it earlier on. It can kind of go anywhere in the syllabus, and so I think this is an appropriate place for it. So we've just finished up talking about all kinds of different applications of integration: differential equations, volumes, work, area, all of these things. And in each of these examples, we set up integrals for volumes and work and things like that. Or with differential equations, we looked at an expression and we ended up using integrals and solving integrals to come up with final answers. And all of this depended on our ability to be able to solve integrals from chapter 6. So it turns out that we kind of have a problem. And the problem is this. Integral from 0 to 1 of e to the negative x squared dx. This is a problem. When I look at this integral, I start to get really excited because I'm like, oh, look, u substitution, I'm going to let u be equal to negative x squared, and then I take my derivative and I have negative 2x and I cannot cancel it. And then I say, oh, well, let me do integration by parts. And so let's see here, u, v, dv, and du, and I start to think about things here, and well, algebra, I mean, this is an exponential, so I really don't want that to be my u, because that's very last in the Lie acronym. And so if I did u, I'm going to try it. Let's see what happens here. dv is dx, so v is equal to x. And du is going to be derivative of the outside, keeping the inside the same, times the derivative of the inside. So we have e to the negative x squared times negative 2x dx. And so our uv minus the integral of v du is going to look like e to the minus x squared times x minus the integral of v, which is an x, times e to the minus x squared times negative 2x dx. And then this part over here, this integral, well, we've got plus 2x squared e to the minus x squared dx, and that just made it worse than when we started. Okay? And so I really want to cry on this particular problem because integration by parts didn't work, u substitution doesn't work, and in fact, it turns out that there is absolutely positively no integration technique that will solve and find an antiderivative for e to the minus x squared. Which is really, really weird. There does not exist an elementary antiderivative for e to the minus x squared. What do I mean by elementary? I mean something that you can write down in a nice closed form. So this integral is a non-elementary integral. Meaning that there is no nice antiderivative. No nice antiderivative for e to the minus x squared. Now, this is a perfectly legitimate question to ask. I mean, finding the area under e to the negative x squared, well, I can definitely graph e to the negative x squared. That's not hard to graph. And if you have a calculator, you might want to pull it out and graph that function. It's a nice symmetric function. When x is equal to 0, then we're at a height of 1. And otherwise, in both directions, this function kind of falls off. And, I mean, to look at the integral from 0 to 1 of e to the minus x squared dx, well, we're talking about finding the area between x is equal to 0 and x is equal to 1. And so that's a perfectly legitimate question. And not only is it legitimate in the sense of the geometry here, but something that you might notice about this curve right here is that it looks kind of like a bell curve. And e to the minus x squared is part of the formula for the standard bell curve. And so this is a really important curve that people want to know an awful lot about. And we can't even find an antiderivative for this thing. And it's a total bummer. Okay. And so what do we have to do? Well, what we need to do to solve integrals like this, and to solve, there's tons of them. I mean, the number of integrals that we can actually solve analytically, like we did in chapter 6, the sliver about this wide, all that work you did, sliver about this wide in a room this size. Okay? And so there's a ton of these guys that show up where we cannot find an antiderivative, and so what we have to do is to find this area, we need to calculate the area numerically, meaning that we're going to need to find approximations. So we're going to use our idea of integrals, the idea where we break this up into rectangles, but we're not going to be able to use our fundamental theorem, which says find the antiderivative and plug in the endpoints.
It's just Riemann sums.
So that's exactly right. We're going to get, so it starts out as a Riemann sum, and we're going to make it a little bit more sophisticated than just straight up
Trapezoid?
Yep, so we can use trapezoids, we can even approximate. So this is what we're going to see a little bit next week, and then briefly after the break as well, is that we're going to want to do things like break this up into rectangles, break it up into trapezoids, maybe even approximate this with quadratic functions rather than just straight lines. And so we're going to be doing some approximation techniques. And so for those of you who like who are planning to be applied, this is a big section for you. Okay, that's all I have to say for today. Let me give you some practice problems for section 6.